Hello everyone. Today we will be talking about another algorithm design technique called greedy algorithms. Similar to the dynamic programming, the problem that can be solved by greedy algorithms also has two properties. First one is similar to the dynamic programming, the optimal substructure property. We all know a problem has optimal substructure if an optimal solution to the problem is composed of optimal solutions to its subproblems. The second property is called greedy choice property. What it means, you will have to make decisions in various steps of solving the original problem. When choices are considered, the choice that looks the best in the current problem is chosen, without considering the results from the subproblems. We will also discuss a problem with the greedy strategy. That is, greedy algorithms do not always yield the optimal solutions. So, you need to prove that the greedy strategy you choose will always yield the optimal solution. Otherwise, it's just an heuristic. Let's discuss the greedy algorithm design technique with an example. The problem we will be talking about is called make change. Here you have some coin denominations. For example, 1, 5, 10, 25. The problem states that you need to make a change of n dollars using fewest number of coins. One naive solution can be try all possible combination of coins and choose the one that requires the smallest number of coins. We can formulate a recursive algorithm as follows. We can call a recursive function change, which takes a parameter n, which means change n is the fewest number of coins needed to make the change for n. As we are trying to solve this one as a recursive solution, what can be the base cases? The base cases can be if we are asked to make change for any n that is equal to any of the coins we have, then the result should be 1. That means change 1 equals change 5 equals change 10 equals change 25 equals 1. Why? We can just use one coin in this case. Here we need to think about another base case. What happens if we are trying to find change of n when n is less than 0? In that case, the answer should be infinite. That means if n is less than 0, no number of coins will be able to give us the result for this problem. If n is not equal to any of the denominations, then we can solve the problem recursively. We will recursively solve the following subproblems. We will try all possible ways to solve the problem. That means we will solve change n minus 1, change n minus 5, change n minus 10, change n minus 25. If we know the answer from these subproblems, then we can take the minimum of them. To get the solution for change n, we can add 1 to the minimum of these subproblems to get the actual result. So what would be the runtime of this solution? I encourage you to think about it and try to come up with the runtime of this algorithm. If the optimal solution of n cents consists of q quarters, d dimes, n nickels, and p penny, that means then we can use the formula n equals 25q plus 10d plus 5n plus p will be the optimal solution for n cents. And the number of coins needed, change n or Cn, is q plus d plus n plus p. In our previous example, when n was 89, we used 3 quarters, 1 dimes, 4 pennies. That means 89 equals 25 times 3 plus 10 times 2 plus 1 times 4. How can we prove that our strategy always gives us the optimal answer? In other words, the fewest number of coins. Here is how. First, we need to recall that our strategy always try the higher denominations first. before trying out any lower denominations. That means we always try the quarter first before going to try any dime, nickel or penny. Now we are ready to prove that our strategy yields us an optimal solution. The way we will do that, we will prove these three statements. P should be less than 5, 5n plus P should be less than 10, and 10d plus 5n plus P should be less than 25. So how does these three statements prove that the whole algorithm gives us the optimal solution? Let's consider what happens when P is greater than 5. Suppose P is greater than equals to 5. In that case, if we had P is greater than equals 5, we can get a better solution by replacing them with a nickel. After replacing them using a nickel, still if P is greater than equals to 5, we can replace again until P gets to 4 or less. If you remember, before going to use any penny, we try to use nickel. So this is what we were doing. So in that case, our solution will never gives a solution when number of penny is greater than or equals to 5. Using our strategy, we will always get 5n plus p less than 10. So what happens if that is not the case? That means what happens if we get 5n plus p greater than or equals 10? In that case, we can replace two nickels with one dime to get a better solution. Also, our solution will always yield that 10d plus 5n plus p should be less than 25. What happens if that is not the case? If 10d plus 5n plus p is greater or equals 25, there can be two cases. Case 1, if we had one nickel, we could replace one nickel and two dimes with one quarter. In case 2, if we had no nickels, then we at least have 3 dimes. Now we can replace 3 dimes with 1 quarter and 1 nickel. And as we always try the bigger denomination first, that means we always get the better solution instead of getting more number of coins. So we have just proved that for the denomination 1, 5, 10 and 25, our greedy algorithm always yields the best solution. That means the fewest number of coins. At the beginning of the lecture, I told you that not always greedy algorithm can give us the optimal solution. So what will happen if we add another denomination to our coin set? The denomination we will add is 20. That means now we have 1, 5, 10, 20, 25. And we will use the same greedy strategy to find out how can we find the fewest number of coins when we are trying to get the change for n equals 40. So we start with 40. The highest number denomination we can use is 25. We are left with 15. Now we can use 10. We are left with 5. In this case, we can use 5 to get to the 0. Here we used 1 quarter, 1 dime and 1 nickel. So number of coins is 3. If we think about the optimal solution should be if we use 2 20-cent coins. So the optimal solution should be 2, but using the greedy algorithm we have discussed in the previous problem, we get 3. So in this case, our greedy algorithm does not give us the optimal solution. I encourage you to think about why it does not yield up the optimal solution in this case. That means what denomination we have in our hand will have an effect on whether our greedy algorithm gives us the optimal solution or not. Now, what can we do? We can use our previously discussed technique, which is dynamic programming. Let's try to find a dynamic programming solution for this problem. Suppose we have the following k coin denominations from D1 to Dk. Cn denotes the minimum number of coins necessary to make change for n cents. As we have discussed earlier, the base case should be for any n that matches with our denomination, the result should be 1. So C D1 should be 1, 1, 1. If n is less than 0, in that case, Cn should be infinite because we cannot make change for that case. In the recursive case, we try to find all possible cases using all possible denominations from 1 to k and get the minimum of all of them. For example, if you had only two coins, 1 and 5, and an amount n to make change, your two choices are make change for n minus 1 or n minus 5 and take the minimum of number of coins needed from A and B and add 1 to that answer to get the change for Cn. So now what we know, we can solve this problem using recursion. But if you try to analyze the runtime of the recursive algorithm, it will be exponential. Instead, we will try to formulate a dynamic table. So again, let's try to use the denomination 1, 5, 10, 20, and 25. We will be using this dynamic programming table. Here, Ci is the number of coins needed to make the change I. From the base case, we know the number of coins needed to make change 1 is 1, 5 is 1, 10 is 1, 20 will be 1, 25 will be again 1. So how many coins we need to make change 2? We know we can make change 1 using 1 coin. Then we can add 1 penny to make the change for 2. So we need 2 coins. Similarly, to make the change for 3, we need 3 coins. To make the change for 4, we need 4 coins. So this came from this cell, this came from this cell, and this came from this cell. This one came from the base case. So again, if we try to make change for 6 cents, then we can use 1 5-cent and 1 penny to make the 6-cent change. That means we need 2. If we want to find how many coins we need to make change of 7 cents, we know that we need 2 coins to make change of 6. That means we can add 1 more penny with it to make change of 7. That means 3. Similarly, 4, 5. If you try to find out all the empty cells here, you can calculate 11 will take 2 coins, 12 will take 3 coins, 4 coins, 5 coins, and 2 coins. Why 2 coins? We can use one 10 cents and one 5 cents. 16 will take 3 coins, 17 will take 4 coins. Next, try to find out the same table but using our recursive formula from the previous page. C1, C2 should be, we know C1 is 1, from the base case C minus 3 should be infinite, and all the other cases should be also infinite. So the minimum should be 2. Similarly, in this case, I will not write down the cases where I will get infinite. I will write down only the case where I will get some result. So here we can see the two versions of the bottom-up dynamic programming for the make change problem. I will be discussing the first one. The second was is almost the same. So at the beginning, we use the base cases to populate all the CI for all the denomination of the coins. If we think about the runtime for the line 3, 4, and 5, as we have k coins, the runtime would be theta k. Next, we have our recursive case. In the recursive case, what we do? We populate n cells. For each cell, we try all possible denomination. What this check does, it eliminates all the infinite combinations. That means when you are trying to make a change of 5 cents, but you are trying the denomination of 10 cents or quarter. In other words, the denomination is too big. So the runtime of this part of this algorithm will be theta of n k. Why n times k? Because we are populating all the cells. When we try to populate one cells, we try k denominations or k coins. That means if we think about the whole algorithm, the runtime should be theta of k plus nk. But most of the time, we will have n which is far more greater than k, which means our algorithm's runtime will be theta of nk.